Today we'll talk about analogical reasoning. Analogical reasoning involves understanding new problems in terms of familiar problems. It also involves addressing new problems by transferring knowledge of relationships from known problems across domains. We introduced the notion of transfer previously in explanation-based learning. We also have talked about case-based reasoning. Today we'll talk about transfer in a much more general manner. We'll start by talking about similarity, then revisit case-based reasoning. Then we'll talk through the overall process of analogical reasoning, including retrieval and mapping and transfer. Then we'll close by talking about a specific application of analogy called design by analogy. To illustrate the notion of similarity, let us consider an example. Consider that a woman is climbing up a ladder. Here are 7 situations. Can you please rank these 7 situations by their order of similarity to the given situation? David, what was your answer?
So I said that the two most similar were the woman climbing up a stepladder and the woman climbing a set of stairs. I said the woman climbing the stepladder is a little bit more similar because a stepladder is more similar to a ladder than a set of stairs. But in both these situations, we still have a woman and she's still going up some kind of physical artifact. For third, I put an ant walking up a wall. I ranked that as a little bit more similar than a woman climbing the corporate ladder because here there's the same kind of physical motion up something. Here the motion is more metaphorical. But there's also similarity between the real ladder and the corporate ladder, so this could have been ranked higher as well. For the fifth one, I chose the plane taking off into the sky. While it's physically similar to an ant climbing up a wall in that they're both rising, here the degree to which it's rising is much more significant, and the mechanism by which it's rising is different as well. Then the woman painting a ladder is only similar in that there also is a woman and there also is a ladder, so I didn't think that was very similar. And then the water bottle sitting on a desk is not similar at all.
Interesting answer, David. Note that there are several factors in David's answers. In the 2 situations that he thought were most similar to woman climbing up a ladder, there is similarity in the relationship climbing up, as well as similarity between objects, woman and ladder. In contrast, one that he did not think was very similar to woman climbing up a ladder, a woman painting a ladder, although there is some similarity between the objects, woman and ladder, the relationship is very different. Here it is climbing up a ladder, here it is painting a ladder, which are 2 very different activities. Between 1 and 2, we notice that both of them have the same relationship, climbing up, but the object is different. In one case, it is a step ladder. In another case, it is a set of stairs. So one can have similarities in relationships. One can have similarities in objects. Of course, some of you may have different rankings for this similarity than the one David gave, because your background knowledge might be different or your priorities might be different. But the point here is that similarity can be measured along several dimensions. Along the dimension of relationships, along the dimension of objects, along the dimensions of features of objects, and among the dimensions of values of features of objects that are participating in relationships. We'll talk more about this in just a few minutes. We have come across the notion of similarity earlier in this course. When we were discussing learning by recording cases, at that particular point we came across the method of K nearest neighbor. At that point, we found the nearest neighbor simply by looking at the Euclidean distance between the new situation and the familiar situations. We came across the notion of similarity when we were discussing case-based reasoning as well. At that point, we came across at least 2 different methods of organizing the case library. And that in one method, we could simply organize all the cases in an array. Here is an array of several cases in the domain of navigation in an urban area. Each case here is represented by the X and Y location of the destination. A different and smarter method was to organize these cases in a discrimination tree. The leaf nodes of this discrimination tree represented the cases. The root node and the intermediate nodes in the discrimination tree represented discrimination or decisions about the values of specific features. For example, east of 5th Street or not east of 5th Street. Both of these case indexing schemes are based on measures of similarity. In the first scheme, the similarity is based on the similarity between the tags. If a new problem were to come along, it will be more or less similar to one of these cases depending on whether or not its tags match the tags of a particular case here. In the second scheme of the discrimination tree, similarity is based on traversing this particular tree. If a new problem came along, we would use the features of that new problem to traverse this tree and find the case whose features best match the new problem. Note that the new problem and the source cases in all of these examples so far have been in the same domain. Here, for example, both the new problem and the source case are in the same domain of navigating in an urban area. In the previous example, the new problem in the source case was the domain of colored blocks in the blocks world. What happens if the new problem and the source case are not in the same domain? So consider the example of a woman walking up the ladder and an ant walking up the wall. The two domains are not the same. We're talking about woman in one case, ant in another case, a ladder in one case, a wall in another case. Yet, there is some similarity. Situations like this, where the new problem and the source case are from different domains, lead to cross-domain analogies. So the question now becomes, how can we find the similarity between the new problem, the target problem, and the source case if they happen to be in different domains? To dig into this issue of similarity between a target problem and a source case in different domains, let us look at another example. Let us suppose there is a patient who has a tumor in his stomach. There is a physician who has a laser gun. She knows that if the laser light were to shine on this tumor, the tumor will be killed and the patient will be cured. But the physician has a problem. The laser light is so strong that it will also kill all the healthy tissue on its way to the tumor, and thereby killing the patient. What should the physician do? This is actually a very famous problem in cognitive science. It was first used by a psychologist called Dunker around 1926. Or what do you think the physician should do in this situation? Take a moment and think about it. We'll return to the physician and the patient example in just a minute. First, let me tell you another story. Once there was a kingdom ruled by a ruthless king. There was a rebel army approaching the fortress in which the king lived. But there was a problem. The king's men had mined all the roads approaching the fort. As a result, if an army was to walk over the roads, their mines would go off and the soldiers would be killed. So what did the army decide to do? The army decided to decompose itself into smaller groups so that each group could come from a different road and reach the fort at the same time. Because each group was small enough, the mines on the roads did not go off. The soldiers were able to attack the fort at the same time and overthrow the bad king. Now let us go back to the problem of the physician and the patient. What do you think now? Has your answer to the problem changed? Some of you indeed may have changed your answer because of the story I told you about the king and the rebel army. One solution to this problem is that the physician may divide a very intense laser beam into several smaller, less intense beams. As these beams come from different directions, they do not harm the healthy tissue. However, they reach the tumor at the same time and manage to kill the tumor. You will note that this is an example of cross-domain analogy. Here, the target problem had to do with the physician and the patient. The source case had to do with the king and the rebel army. The objects in the two situations were clearly very different. In one case, we had the physician and the patient, the laser beam and the tumor. In another case, we had the king and the rebel army, the fort and the mines. But some of the relationships were very similar. In capturing the fort case, we had a resource, the army, which was decomposed into several small armies, which was sent to the goal location at the same time. We took this pattern, we took this strategy, abstracted it out, and then applied it to the patient and physician example. The physician used the same strategy. The resource decomposed it into several smaller resources and sent it to the goal at the same time. Now you can also see why the ant climbing a wall is similar to a woman climbing a ladder. The objects are different, ant and wall, woman and ladder, but the relationship is similar, climbing up. In cross-domain analogies then, the objects and the features and the values of the objects can be different. The similarity is based on the relationship. It is the relationship that is important. It is the relationship that gets transferred from the source case to the target problem. We can think of a spectrum of similarity. At one end of the spectrum, the target problem and the source case are identical. At the other extreme end of the similarity spectrum, the target problem and the source case have nothing in common. We can evaluate the similarity between the target problem and the source case in several dimensions. In terms of the relationships occurring in the source case and the target problem, in terms of the objects occurring between the two, in terms of the features of the objects, and in terms of the values that the features of the objects take. At the end of the spectrum, where the target problem and the source case are very similar, the relationships, objects, features, and values are all similar. At the other end, the values, features, and objects may be different, but the relationships are similar. If the relationships too were different, then there would be nothing in common between the target problem and the source case. When the relationships, objects, features, and values are all similar, then that is an example of recording cases, and we have come across it. An example of that was from the colored blocks in the blocks world. When the similarity between the target problem and the source case is along the dimensions of relationships and objects, but not along the dimensions of values or values and features, then that's an example of case-based reasoning. We discussed this method in the domain of navigation in urban areas. The objects or the concepts between the target problem and the source case being the same means that the domains are the same. So case-based reasoning is within domain analogy. In analogical reasoning in general, objects in the target problem and the source case too might be different. We saw an example of analogical reasoning in the Duncker radiation problem when we were talking about cross-domain analogical transfer. Actually, recording cases and case-based reasoning are also examples of analogical reasoning, except that they occur in the same domain. The target problem and the source case is in the same domain, which is why we considered them earlier. By analogical reasoning here, we mean cross-domain analogical transfer, as in the Duncker radiation problem. Analogical reasoning allows us to look at new problems in terms of familiar problems. It also allows us to transfer knowledge from familiar problems to new problems. A high-level process for analogical reasoning is shown here. It consists of 5 major phases: retrieval, mapping, transfer, evaluation, and storage. We'll discuss all 5 stages in detail. Let us compare for a moment the process for analogical reasoning in general with the process for case-based reasoning within domain analogical reasoning that we discussed earlier. Notice that retrieval, evaluation, and storage are common between the two processes. In case-based reasoning, the target problem and the source case were from the same domain. They had the same kind of relationships and the same kind of objects. We simply had to adapt the source case to address the target problem. In analogical reasoning in general, the target problem and the source case need not be from the same domain. When they are not from the same domain, we can't just take the source case and adapt it. We first have to map the target problem and the source case. That is, we need to address the correspondence problem. What in the target problem corresponds to what in the source case? As an example, the laser beam in the target Duncker radiation problem corresponds to the rebel army in the source case. Once we have mapped the concept and relationships in the target problem to the concept and relationships in the source case, then we can try to transfer some of the relationships in the source case to the target problem. We can first abstract those relationships and then transfer them to the target problem. As an example, in the Duncker radiation problem, we first did the alignment. That is, we addressed the correspondence problem. What in the target problem corresponds to what in the source case? Then we took the relationship and abstracted it. The relationship in that case was take the resource and decompose it into several smaller resources and send them to the goal at the same location. That particular relationship, that particular pattern is what we abstracted and transferred to the target problem. Note that this is just one theory of analogical reasoning. In other theories, some of these boxes are configured differently. For example, in another theory, mapping is a part of retrieval. You do mapping in order to do retrieval. Let us look at analogical retrieval more closely. Once again, we have come across this idea earlier. We did analogical retrieval in recording cases by the k-nearest neighbor method. We did analogical retrieval in case-based reasoning using 2 different methods, the array method and the discrimination tree method. Here, the criteria for evaluating similarity were very clear, as we discussed earlier. Euclidean distance, same tags, as well as placement in this discrimination tree. The question now becomes what criteria should be used to decide on the similarity between the target problem and the source case, given that they come from different domains. On surface, there seems to be little similar between the two. None of the objects is similar. None of the values or features is similar. Yet, there is a deep similarity there. We can distinguish now between superficial similarity between 2 situations and deep similarity between 2 situations. Superficial similarity deals with features of objects or counts of objects or objects themselves. Deep similarity deals with relationships between objects or sometimes relationships between relationships. Examples of this arise from the Raven's test, with which you are already familiar. Features here refer to the size of the square, the size of the circle, or perhaps whether it's a hollow square or a solid dot. The count refers to the number of squares or the number of circles in a particular image. Objects here refer to circles and squares and dots. Let us look at relationships between objects. Two situations are said to be deeply similar if the relationship between the objects is similar. As an example, A and B are similar in that the dot is outside the circle here and the square is outside the circle here. A and B are also similar in that the dot is above the circle here and the square is above the circle here. What about relationships between relationships? Let us compare A and B. In going from A to B, the dot has disappeared and the square has come outside the circle and become bigger. Now we can compare this relationship between A and B with some of the relationship between a C and a D, in which too some object might be disappearing and another object which was in the center of the circle comes out of the circle. I'm sure you have come across problems like that on the Raven's test. This is an example of a binary relationship, a relationship between two objects. This is an example of a higher order relationship, a tertiary relationship if you wish. This is a relationship between objects. You might even say that these are examples of unary relationships. These are just examples of objects and their features and counts. In general, as we go from unary relationships to binary relationships to tertiary relationships to even higher order relationships, the similarity becomes deeper and deeper. This means that mind decides two situations to be more similar if the similarity is at the level of relationships between objects rather than simply at the level of objects or features or counts or objects. Semantic similarity deals with conceptual similarity between the target problem and the source case. If you recall the original exercise that David had answered, in that exercise, a woman climbing up a ladder is conceptually similar, is semantically similar to a woman climbing up a stepladder. The same kind of concepts occur in both situations, woman and stepladder or ladder. Pragmatic similarity concerns with external factors, factors external to the representation, such as goals. As an example, in the Dunker radiation problem, the physician had a goal of killing the tumor, which was similar to the goal of capturing the fort in case of the rebel army and the king. Pragmatic similarity refers to similarity of external factors, factors external to the representation, such as similarity of goals. In the Dunker radiation problem, for example, the physician had the goal of killing the tumor, which was similar to the goal of capturing the fort in case of the rebel army and the king example. The third measure of similarity is structural similarity. Structure here refers to the structure of representations, not the physical structure. The structural similarity refers to similarity between the representational structures of the target problem and the source case, and we'll look at an example of this in just a few minutes. Note that one can assign different kind of weight to these three measures of similarity. So some theories of analogy focus on structural similarity. Other theories of analogy focus on semantic and pragmatic similarity. That is also why you may have given slightly different answers to the questions in the first exercise than David did. Let us do another exercise together now that we know about deep similarity and superficial similarity. Consider the situation again: a woman is climbing up a ladder. Given the 7 situations, mark whether each of the situations is deeply similar or superficially similar to this given situation. Note that some might be both and others might be neither. What do you think, David?
So perhaps unsurprisingly, I said that the two most similar situations in my original answer were both deeply and superficially similar. A woman climbing a stepladder is both deeply similar in that the relationships are the same, and superficially similar in that the woman and the ladder are somewhat similar. I also said that the woman climbing a set of stairs was both deep and superficially similar. We still have a woman climbing in both. And I said that a set of stairs is somewhat superficially similar to a ladder in that both are designed to allow someone to ascend, although some others might say that that's not superficially similar. Then I said that the other three that involved rising in some way were all deeply similar as well. The plane taking off into the sky, the woman climbing the corporate ladder, and the ant walking up the wall were all deeply similar to me because all involved this relationship of climbing. I said that the woman painting a ladder was only superficially similar, which is why it was one of the lowest rated in our original exercise. And finally, the water bottle sitting on a desk is neither deeply similar nor superficially similar, because nothing is the same between those two situations.
This is good, David. Once again, different people may give different answers to this exercise. Why they may do so, well, let's examine it next. Many science textbooks in middle school or high school explain the atomic structure in terms of the solar system. Here's a representation for the solar system. Here is a representation for the atomic structure. Let us see how this model of the solar system helps us make sense of the atomic structure. We'll use this example often going forward. In this representation of the solar system, these arrows are denoting causality. So the sun's mass is greater than the planet's mass, which causes the planet to revolve around the sun. Similarly, for the atomic structure, there is a force between the nucleus and the electron, and that causes the nucleus to attract the electron and the electron to attract the nucleus. Given these two models, what are the deep similarities between them? What do you think, David? What are the deep similarities here?
So I picked that 3 of these are deep similarities. In both, there's something revolving around something else, the planet revolving around the sun and the electron revolving around the nucleus. In both, there's a force between two objects, a force between the sun and the planet, and a force between a nucleus and an electron. And in both, two objects attract each other. All 3 of these are based on relationships, the revolution, the force between two objects, and the attraction between two objects. I didn't pick the other 3 because while these 2 are true, they don't represent deep relationships. And while this is actually true, it's not actually captured in our representation. So this isn't part of our knowledge base for the purpose of this problem.
Now we can see why these textbooks write about the solar system and the atomic structure in such a way that these relationships become salient. They help us make sense of the atomic structure by pointing to the deep similarities between the relationships that are occurring in the atomic structure and the relationships that are occurring in the solar system. Now let us consider analogical mapping. The problem here is called the correspondence problem. There are a number of objects and relationships in this target problem. There are a number of objects and relationships in this source case. What in the target problem corresponds to what in the source case? If we can address the correspondence problem, if we can say, for example, that the laser beam corresponds to the rebel army, then we can start aligning the target problem in the source case so that it makes the deep similarities between relationships salient. Note that there are several objects in the target problem and several in the source case. In principle, any of these objects in the target problem could correspond to any of the objects in the source case. In which case, we would have a M to N mapping, and that becomes computationally inefficient. Yet you and I often do not have much of a problem deciding that the laser beam must correspond to the rebel army. How do we do it? And how can we help AI agents make similar kind of correspondences? Our answer is, we'll make use of relationships. In fact, we'll make use of higher order relationships whenever possible. We'll give precedence to higher order relationships over other relationships. As a unary relationship, we might say that there is a patient as a person here and king as a person there. As a binary relationship, we might say that a physician has a resource, the laser beam, and that a rebel army has a resource, the army itself. As a higher order relationship, a tertiary relationship between, say, that between the goal and the resource is an obstacle, the healthy tissue in this case. Similarly, between the goal and the resource is an obstacle, the minds in this case. We'll focus on the higher order relationship there. That's where the deepest similarity between the two situations lies. This is how we know to map between the king and the tumor and not between the king and the patient. Although the king and the patient are superficially similar, the deeper similarity lies in viewing the king and the tumor in terms of goals, which need to be cured or captured using a resource when there is an obstacle in between them. Let us do an exercise on deep relationships. Let's get back to our example of the solar system and the atomic structure. Let us suppose that you're given this representation of the solar system and this representation of the atomic structure. How would you map the solar system to the atomic structure? What choices did you pick, David?
So there's a few different ways we could do the mapping between the sun and the planet on the left and the nucleus and the electron on the right. If we look only at the top half of each representation, all we can really say is that the sun must map to one of them and the planet must map to one of them. Because these relationships are symmetrical, if I don't consider the bottom half, it wouldn't matter which is which. If I look at the bottom half of the representations, however, it tells me which part of the solar system must correspond to which part of the atomic structure. The planet revolves around the sun and the electron revolves around the nucleus. So the planet and the electron must correspond because both are doing the revolving, and the sun and the nucleus must correspond because they are the centers of the revolution. So the sun corresponds to the nucleus, and the planet corresponds to the electron.
This is right, David. Another thing to take away from here is, note the depth of understanding it requires in order to be able to make the right kind of correspondences. If one did not have the right kind of model for the solar system and the atomic structure that captures the deep relationships, then the mapping may not be done. The alignment wouldn't work, and we would not be able to understand the atomic structure in terms of the solar system. Thus, models, deep and rich models of the two systems, the target problem and the source case, are essential to deciding how to align them, how to map them, and as we'll see in a moment, what to transfer and how to transfer it. Now let us consider analogical transfer. So given this target problem, analogical retrieval has led to this source case. Given a model of the target problem and a model of the source case, analogical mapping has also occurred. Correspondence has been established. Thus, we now know that the king corresponds to the tumor, not to the patient, and that the rebel army corresponds to the laser beam. For the source case, we also know the solution. The rebel army divided itself into smaller groups, and the smaller groups all arrived at the fort at the same time. Now the question becomes, how can we transfer this solution to our original target problem? From the source case now, we're inducing a pattern of relationships, a strategy. In this case, the pattern is that if there is a goal, capturing the king, and a resource, the rebel army, and an obstacle between the resource and the goal, the mines on the road, then decompose the resource into several smaller resources and send them to the goal from different directions at the same time. This abstract pattern is now transferred to the target problem and instantiated. Because we know that the goal is the tumor, the resource is the laser gun, and the obstacle is the healthy tissue, we know what to do. We must decompose the resource, the laser gun, into smaller pieces, smaller, less intense laser beams, and send them to the tumor, the goal, at the same time from different directions. This is how we can transfer the problem-solving strategy from the source case to the target problem. Note that this transfer depended upon the correct mapping, the correct alignment between the target problem and the source case, which in turn depended upon the retrieval of the source case corresponding to this target problem. Note the important role of goal here. The goal was to capture the king. So this is an example of pragmatic similarity, where a lot of similarities at the level of the goal, capturing the king, curing the tumor. Let us do an exercise on analogical transfer together. Back to our example of the solar system and the atomic structure. Given this representation of the solar system and this representation of the atomic structure, what would be transferred from the solar system into the atomic structure model?
So I said that we transfer three things. First, we're going to transfer the idea that the force between the nucleus and the electron is caused by the fact that both the nucleus and the electron have mass. We notice that the relationships up here were similar to the relationships over here, so we're going to infer that the explanation is the same as well. So the nucleus has mass, and the electron has mass, and those are going to cause the force between the nucleus and the electron. We're also going to transfer the idea that because the electron revolves around the nucleus, that means that the nucleus must have a greater mass than the electron. The planet revolved around the sun because the sun's mass was greater than the planet, so the electron must revolve around the nucleus because the nucleus's mass is greater than the electron's. We wouldn't transfer the idea that the nucleus is a sun or that the electrons are planets, because those take the transfer a little bit too literally. We also wouldn't transfer the idea that the nucleus attracts electrons, or the electron revolves around the nucleus, because those were already in our original representation. So we end up with this. The nucleus and the electron both having mass causes the force between them, and the nucleus's mass being greater than the electron's mass causes the electron to revolve around the nucleus.
That's a smart answer, David. Recall that originally I had said that I'll explain structural similarity, and I have not done it so far. I'm going to use this particular example and David's answer to explain it now. Given the solar system as the source case and the atomic structure as the target problem, we can see that there is little semantic similarity between them. The kinds of objects that are occurring in the solar system are not at all like the kinds of objects that are occurring in the atomic structure. We can also see that pragmatic similarity is not a major issue here. We are not talking about the goal of the solar system or the goal of the atomic structure. Although we might have the goal of understanding the atomic structure in the solar system, there is nothing in the solar system or in the atomic structure which has a goal. Yet, David was able to answer this question correctly. This is because of structural similarity. Let us consider the top part of the model of the solar system. You can think of this top part like a graph. The vertices in this graph correspond to objects and their properties. The edges in this graph correspond to relationships, such as force between sun and planet, or sun attracts planet and planet attracts sun. Once again, this graphical representation of the model of the atomic structure, the vertices representing the objects and the features, and the edges are representing the relationship between the objects. Although there is little semantic similarity or pragmatic similarity between the two situations, we can see a structural similarity, a similarity in the structure of the graphs. Because this part of the graph of the representation of the solar system is similar to this part of the graph of the representation of the atomic structure, we can therefore infer that we can transfer this part of the graph of the solar system to infer this part of the graph of the atomic structure. Structural similarity then captures relational similarity. What is common between these two situations is neither the objects nor the goals. What is common here is the relational similarity, and that is what structural similarity captures. Let us briefly talk about evaluation and storage. This evaluation and storage steps in analogical reasoning are very similar to the evaluation and storage steps in case-based reasoning. Analogical reasoning by itself does not provide guarantees of correctness, so the solution that it proposes must be evaluated by some manner. For the Dunker radiation problem, for example, we may evaluate the proposed solution by doing a simulation. Once the evaluation has been done, then the new problem and its solution can be encapsulated as a new case and stored back in memory for later potential reuse. To return to the Dunker radiation problem as an example, once we have the solution of decomposing the laser beam into several smaller beams and sending them to the tumor at the same time from different directions, we can do a simulation of the solution and see whether that is successful. If it is, then we can encapsulate the target problem and the proposed solution as a case and store it in memory. It might be useful later. It could potentially become a source case for a new target problem to come later. Once again, in this way, the AI agent learns incrementally. Each time it solves a problem, the new problem and its solution becomes a case for later reuse. It is often useful to look at specific problem domains, both to see how we can apply current theories of analogical reasoning to them, and also to see how we can use those problem domains to build new theories of analogical reasoning. So let us turn now to the domain of design. In design, there is a new movement that is sometimes called biologically inspired design or biomimicry. This movement is pulled by the need for environmental sustainability and is pushed by the desire for creativity and innovation in design. On the top left here is a picture of the Shinkansen 500 train in Japan. This is a bullet train. It's called a bullet train because of the shape of its nose. This particular shape is inspired by the shape of the beak of the kingfisher. The story goes something like this. Japanese railway engineers were interested in building faster trains. However, they had a problem. These trains had to go through tunnels. And as they went through tunnels, they created shock waves, which created a lot of noise, bothering the neighbors. The shock wave was created because outside the tunnel and inside the tunnel were two different mediums. By serendipity, the railway engineers looked at how the kingfisher goes from the medium of air into a medium of water, dips its beak, and catches its prey. The shape of its nose allows us to create a smaller shock wave. They use the same principle to create the design of the nose of the bullet train. Shinkansen 500 travels faster than previous trains and also makes less noise than previous trains, mostly because of the nose shape. Another example often cited in biomimicry is the example of a Mercedes-Benz box car, designed by inspiration to the box fish. Notice this biologically inspired design entails analogical reasoning. There is a target problem, there is a source case. There is cross-domain analogical transfer. To illustrate analogical reasoning in design, or analogical design, we'll talk about a specific problem. Let us suppose that you design a robot that can walk on water. Nature already offers several examples of organisms that can walk on water. This is a picture of the basilisk lizard, which can walk very well on water and catch its prey. Recall that we said earlier that for analogical mapping and transfer to occur well, requires a deep understanding of the source case and the target problem. That is true here as well in case of analogical design. We require a deep understanding of the locomotion of the basilisk lizard in order to be able to design a robot that can walk in water inspired by the design of the basilisk lizard. Here is a model of the basilisk lizard. This model is sometimes called structure, behavior, function model. This particular picture doesn't show the structure, it just shows the function and the behavior. The function is shown at the top here. It is shown by its initial state and its goal state, and this function is achieved by the behavior shown here. The behavior is represented as a series of states and transitions between those states. We'll not talk about the representations in more detail here. Readings given in the class notes give these representations in a lot more detail if you're so interested. Recall that we started with the problem of designing a robot that can walk on water. Let us suppose that that particular target problem results in the retrieval of a source case of a robot design that we've already encountered, one that can walk on ground. Now the question becomes, how can we adapt this particular design of a robot that can walk on ground into a robot design that can walk on water? Let us now suppose that we reuse this particular problem of designing a robot to walk on water as a probe into the case memory. And now the case returns to us the design of the basilisk lizard. That might happen because the design of the basilisk lizard is indexed by its functional model, walk on water. So there is a pragmatic similarity between the two. We now have the design of a robot that can walk on ground, and we have the design of a biological organism, the basilisk lizard, that can walk on water. For the basilisk lizard, we also have a complete model, a complete explanation of how its structure achieves its function. Now that we have a partial design for the robot, this is the design of the robot that can walk on ground, and we have a design of an organism that can walk on water, we can try to do an alignment between these two. This alignment will be based on the similarity between relationships. Clearly, the objects here and the objects there are very different. Once we have aligned these structural models of the robot that can walk on ground and the basilisk lizard that can walk on water, then we can start doing transfer. We can transfer specific features of the structure of the basilisk lizard, for example, the shape of its feet, to this model of the robot that can walk on ground in order to convert it into a robot that can walk on water. Having constructed a structural model for this robot that can walk on water, then we can try to transfer the behavioral model and then the functional model. And in this way, we have a complete model of a robot that can walk on water along with an explanation of how it will achieve its function. This is sometimes called compositional analogy. We first do mapping at the level of structure, and that mapping at the level of structure helps us transfer some information. That, in turn, allows us to transfer information at the behavioral level. Once we have transferred information at the behavioral level, we can climb up this abstraction hierarchy and transfer information at the functional level. We can now revisit our computational process for analogical reasoning. Initially, we had presented this particular process like a linear chain: retrieval, mapping, transfer, evaluation, and storage. In general, however, there can be many loops here. We may do some initial mapping, for example, that may result in some transfer of information. But that transfer then may lead to additional mapping, and then to additional transfer, and so on. Here is another brief example from biological inspired design. In this case, we want to design a robot that can swim underwater in a very stealthy manner. This particular function of swimming underwater in a stealthy manner reminds a design team of a copepod. A copepod is a biological organism that has a large number of appendages. It moves underwater in such a way that it generates minimum wake, especially when it moves very slowly. On the other hand, when it moves rapidly, then the wake becomes large. When the wake is small, then its motion is very stealthy. When the wake is large, its motion is no longer stealthy. Analogical transfer of knowledge about this particular copepod gives us a design for the microbot for slow velocities. This analogy decomposes our original design problem. We had the original design problem as moving underwater in a stealthy manner. Now that we have a design of an organism for moving underwater at low velocities, we are still left with the sub-goal of moving underwater at high velocities. The goal of designing a microbot that can move underwater in a stealthy manner at fast velocities may remind the design team of the squid. The squid uses a special mechanism like the jet propulsion mechanism to move underwater in a stealthy manner at pretty high velocities. Now we have created the design of a microbot where part of the design comes from the design of the copepod and the other part comes from the design of the squid. Instead of borrowing the design from one source case, we are borrowing parts of the design from multiple source cases. This is a compound analogy. Notice that there is a problem evolution going on. We started with one problem. We arrived at a partial solution to that. which then leads us to a problem evolution, a problem transformation. We now have a new understanding of the problem. So in this example, we saw how we first did analogical retrieval of the copepod organism, then mapping, then transfer. That then led to additional retrieval, in this case of the squid. Once again, this process is not linear. Just like we can iterate between mapping and transfer, similarly we can iterate between transfer and retrieval. Evaluation too can play a very important role in the iterative loops in this analogical reasoning process. One can use several different methods for doing evaluation. In the robot that can walk on water, for example, we can do a simulation, or we can build a physical prototype. If the evaluation succeeds, then well and good. We can encapsulate the target problem in a solution as a case and store it in case memory. But if the evaluation fails, we may need to revisit transfer and see whether we want to transfer some other knowledge, or revisit mapping and perhaps align things differently, or revisit retrieval and perhaps try to retrieve a different source case. As an example, supposing that the evaluation shows that the robot that we designed for walking on water is a little too heavy. In that particular case, we may change the problem specification and retrieve a different kind of organism that perhaps is a little lighter. Let us suppose that we evaluate the design of the robot that can walk on water and find that the design is a little too heavy. In that case, we can go back to the transfer stage and see whether we can transfer some other relationship that might make the robot a little lighter. Or we can go back to the mapping stage and see whether we can align the source case and the target problem slightly differently so that we can transfer a different relationship. Or alternatively, we can go back to the retrieval stage and try to retrieve a source case, a different kind of biological organism altogether. Thus, we see that the process of analogical reasoning is not linear at all. Instead, it can have many different kinds of iterations. Analogical reasoning continues to be an important topic in AI research, and biologically inspired design is becoming one. We provide several readings for both topics in the class notes. There are a number of advanced and open issues in analogical reasoning that are the subject of current research. First, because analogical reasoning entails cross-domain transfer, does it mean that we necessarily need a common vocabulary across all the domains? Consider the example of the atomic structure in the solar system once again. Suppose I were to use the term revolves to say the electron revolves around the nucleus, but use the term rotate to say the planet rotates in an orbit around the sun. I have used two different terms. How then can I do alignment between these two situations? Should I use the same vocabulary? If I don't use the same vocabulary, what alternative is there? Second, analogical reasoning entails problem abstraction and transformation. So far we have talked as if the problem remains fixed, a source case is retrieved and transfer occurs. But often the agent needs to abstract and transform the problem in order to be able to retrieve the source case. A third issue in analogical reasoning concerns compound and compositional analogies. So far we have talked that given a problem, we can retrieve a case and transfer some knowledge from that case to that problem. But often we retrieve not one case and we transfer knowledge from not one case, but from several cases. If you're designing a car, you might design the engine by analogy to one vehicle and the chassis by analogy to some other vehicle. This is an example of compound analogy. But how can we make compound analogy work? In compositional analogy, analogy works at several levels of abstraction. Supposing we were to make an analogy between your business organization and some other business organization. We might make this compositional analogy first at the level of people, next at the level of processes, third at the level of the organization as a whole. This is an example of compositional analogy where mapping at one level supports transfer at the next level. How do we do compositional analogy in AI agents? Fourth, visuospatial analogies. So far we have talked about analogies in which the transfer necessarily engages causal knowledge. But there are a large number of analogies in which causality is at most implicit. We'll consider these visuospatial analogies later in the class. Fifth, conceptual combination. A powerful learning mechanism is learning a new concept by combining parts of familiar concepts. Analogical reasoning is one mechanism for conceptual combination. I have one concept, the problem concept, that of the atomic structure, another concept, the solution concept, the concept of the solar system. I take some part of the solar system knowledge, combine it with my concept of the atom to get a new concept of the atom. If you're interested in any of these issues, I invite you to join the PhD program in computer science.
So how would you use analogical reasoning to design an agent to answer Raven's progressive matrices? This might be a tough question at first because the agents we're designing only operate in one domain, taking the Raven's test. They don't look at other areas. So where could they get the knowledge necessary to do cross-domain analogical transfer? In this instance, instead of the agent doing the analogical reasoning, maybe it's you doing the analogical reasoning. Can you take inspiration from other activities to inspire how you design your agent? Or can you take knowledge from other activities and put them in your agent so that it can do the analogical reasoning? So today we've been talking about analogical reasoning. We started by talking about similarity. As we saw in our opening exercise, similarity is something that we evaluate very easily without even really thinking about it. How can we design agents that can do the same kind of similarity evaluation? We then talked about analogical retrieval, which can be difficult because we're trying to retrieve examples across other domains. How can we structure our knowledge to facilitate this kind of retrieval? How can a system know that given a model of the atom, it should retrieve a model of the solar system? Then we talked about mapping, which is figuring out which parts of different systems correspond. For example, how can we figure out that the troops in the fort example correspond to the lasers in the tumor example? We then talked about transfer, which is moving knowledge from the concept that we know to the concept that we don't. For example, we used what we knew about the solar system to fill in our knowledge of the atom. Then next we talked about evaluation and storage. How do we evaluate our analogies? In the tumor example, we might actually try that medical procedure. But for other analogies, how do we evaluate them? And then how do we store them for future use? Last, we talked about a special kind of analogy, design by analogy, where we use something that we know a lot about to inform our design of something new. We'll talk a lot more about this, especially design by analogy, when we come to the design unit later in our course.
Analogy is often considered to be a core process of cognition. A common example of analogy we encounter every day is that of metaphors. For example, you can imagine someone saying, "I had to break up with her. We had grown very far apart." Far apart here is a spatial metaphor. One of the famous examples of metaphors comes from Shakespeare. All the world's a stage, all the men and women merely players. The theater here is a metaphor for the world. A third connection is the Raven's test of intelligence. The Raven's test is considered to be one of the most common and reliable tests of intelligence. And as you well know by now, it is based entirely on analogies. Analogy is that central to cognition. Please summarize what you learned in this lesson.
Great. Thank you for your answer.